Okay, in this lesson, we're going to talk some more about our electricity terms and also work some sample problems. So first, back to our current, our electrical current. And remember that the variable in the equation that you're going to see for current is an I, and the definition is the flow of charged particles. And the unit that you use for current is amperes, so you're going to use a capital A. The only thing that people get in trouble with in this unit with the math is not paying attention to all the different letters that are used. So for a conventional current, we have a potential difference as long as it's flowing from high potential to low. And the flow, oops, sorry about that. Gotta get my clicks together. The flow is going to stop when the potential difference is equal. So if there's no potential difference, just like the water pump scenario, we're not going to have any flow. And so to keep the current flowing, there must be some type of charge pump. Well, what's a charge pump? Batteries are charge pumps. They're converting chemical energy into electrical energy. Photovoltaic cells, and think about the photo prefix there, it's talking about light energy being converted into electric energy. Generators are another type of charge pump, and they're taking kinetic energy to electric energy. So think about if you're turning a turbine kind of thing, whether it's by wind or water, steam kind of thing. All right, and then remembering our current flow. So you've seen this picture before, but right now we're looking at the arrows and we're noticing how current is flowing from the positive side of the battery around and back to the negative terminal of the battery. Okay, and then we have a couple of different types of currents, DC current and AC current. DC current, if you kind of notice by the pictures, you can already sort of see the definitions. It's just flowing in one direction, okay, like a battery. Whereas alternating current, if you look at the picture, you notice it's going back and forth and back and forth. So it's constantly changing directions. All right, measuring current. So sorry, some of these are coming out of order. So the first thing there is amperes, our unit for measuring current. Remember, our definition is the flow of 1 coulomb per second. So there you have that. And the device that you use to measure current is called an ammeter. Okay, now voltmeters makes more sense. They measure voltage. So make sure you know that an ammeter is what you'd use to measure current and a voltmeter is what you're going to use to measure voltage, because you're actually going to get these type of meters out to do this. Okay, now how to measure voltage and how to measure current. This cartoon explains it, and it's very, very, very important. Okay, so let's look at it. To measure voltage, you touch the meter's lead, so that's little probes that come off of the device, across the lamp or the battery or whatever you're trying to measure. Okay, and measuring it across the lamp is going to measure the voltage drop. So notice how the circuit is all connected, all the wires are connected here, and you're just placing the probes on either side. Okay, now look at how current is different. First part of the cartoon, to measure current, you must break the circuit. That is the number one mistake made when measuring current. It cannot be all connected because current is the flow of the electrons. We need those electrons to actually flow through the meter. Okay, so we must make it flow through the ammeter to be measured. So notice how our little guy here, he's actually attached to the circuit. So if we trace our wires around, our electrons would flow through him. So you have to make sure you do that when you're measuring current. All right, calculating current. We have current in a lot of different equations. One of them is just the simple equation of charge per time. So let's look at a sample problem using that. If we have a lightning strike that has a charge of 10 coulombs and a current of 10,000 amps, how long does it take to strike? So it's a simple equation here. So go ahead and work it and then check back with the solution. So if we have everything placed in the right order, we should have 10,000 for our current equals 10 coulombs of charge over t. And then we need to solve for that variable on the bottom for time. And if we solve correctly, we get 0.001 seconds. Okay, Ohm's law is our relationship between current, voltage, and resistance. Okay, so there's our equation, and let's use that in a sample problem. What's the resistance of a circuit with a 9-volt battery and 3 amp current? So let's work this. So notice if we have everything in the right spot, 3 is our current, so it goes in the I spot, and 9 is our voltage, so it goes where V is, and now we carefully solve for R, our resistance. And we end up getting 3 ohms. Do not forget about the unit. Try to make the best you can, a little omega symbol there. So notice these equations are pretty simple. We just have to be careful with where they all go in. And then now we're going to continue on to part 2 of the lesson.